to infinity of 1 over n squared. Now, this representation by an infinite series is not proper to do algebraic geometry, but integral can do that. Now, it's a simple exercise to derive the following integral formula. We integrate over the square, two coordinates between 0 and 1, so this is the domain of integration. And what do you integrate? Well, I write differential form, dx over dy, to take into account rotation, minus 1 of xy. The trick is to write 1 over 1 minus xy is 1 plus xy plus x squared y squared plus etc. And you integrate term by term. Very easy. And similar formula in higher case. So, but now the property, the integral, so what you're integrating over this domain, coordinate x and y, 0 and 1. 0. But the function you are integrating is 1 over minus xy. And if you look at the singularities of this function, they are on the hyperbola where xy is 1. And unfortunately, this point needs a domain of integration. When I say domain of integration, it has to be taken as closed and bounded in the plane to compact. This point, if you write x equal y equal 1, this becomes infinity. And that's something which is a nuisance. For instance, the integral is absolutely convergent. Why? Because if you can transform it in an absolutely convergent series, so it's absolutely convergent, but it's not, you have to put something of the real world, so real world, the world of real numbers in it, because the integral is absolutely convergent, but not because it's not a Riemann integral of a continuous function. It's a function with a singularity, but you have to use, if you use Lebesgue integration, of course, it gives you for nothing this condition. So, but then the difficulty is there. And then this difficulty is resolved by the following trick. You introduce a new, instead of having two coordinates, you introduce a third coordinate, which is minus 1x over 1 is xy. And therefore, if you eliminate this, you have three coordinates and an equation which looks like 1 plus xyz is x plus z. So it's a polynomial equation in three space, and the domain of integration is given by the following inequalities. You are on the surface, and your x is between 0 and 1, y is between 0 and 1, and consequently z is between 0 and 1. So the domain of integration is well defined by inequality, and algebraic equality inequality. And then you have, it's a simple exercise to transform the integral into, we integrate now over y squared dx dz plus dy dz plus yz dx dy. That means there is no more singularity now. All the coefficients are polynomial and finite at every point. And, okay, that's a trick. A double integral of this kind over some domain of integration, which is called delta. So the point is that if you can reduce zeta 2 can be reduced by this trick, which corresponds geometrically to blow up this singular point. It's a well-known procedure in algebraic geometry. You reduce it to an integral of a form which has no singularity over a domain which is compact, real in the real domain. Okay. So that kind of integral is called a period. A period. And now this period, well, these were defined by Zaghir, Don Zaghir, of Bonn and Collège de France, and Maxime Kontsevich in 2002. They define a certain class of period, certain class of integral, which have interesting properties. And of course, in order to have interesting arithmetic properties, you need that all the coefficients which come into the equation or in the differential form, all the numerical coefficients should be rational numbers, or even algebraic number would do also. So that's a period. Now, the point is that we have been, a number of people have been studying what is called MZV, multiple zeta value, which are generalization of this series. For instance, a series which was already known to Euler, zeta AB is a sum of 1 over m power A, n power B for 0 smaller than m smaller than n. And you can imagine higher dimensional expression of this kind. Instead of having a summation over two variables, you have a summation over many integral variables. So these numbers have been extensively studied as generalization of the value of zeta values. And they have a lot of properties. Let's say zeta AB plus zeta BA is zeta A plus B minus zeta A zeta B. Euler knew that. And it's a simple manipulation of infinite series. There are other properties which are more subtle, which depends on the representation by integral of such numbers. So all these numbers correspond to periods. All these can be represented as integral of the proper kind. And okay, now we are not completely happy with periods.
I think the right side is switched order.
Right. Thank you. Thank you. Okay. So I usually write it zeta A, zeta B. This is the sum of theta. Okay. So that's it. So now we want to have a notion of motivic period. It's a zeta MAB, which is obtained as follows. There are two definitions, one by Zagir and Kontsevich, which says that when you manipulate this integral, you can do numerical analysis, calculate them with decimal, etc. But you can do something a little more formal. That means you allow only some transformation rule. For instance, in such a double integral, you can make a change of variable, suitable change of variable. It doesn't change the result. You can, if you multiply two such integrals, the Fubini theorem tells you that a simple integral multiplied by a simple integral is double integral, etc. And of course, what you integrate is linear with the result of integration is linear with respect to what you integrate. And also, if you subdivide the domain into two pieces or three pieces, the integral splits into many steps. And so, and integration by part. So there are a number of rules of that kind. There are a number of rules of that kind. And of course, any integral, you can say the following: you have programs. You want to calculate a program. Then you start with a formula, and then you make some transformation, which are given in the program. You start with a certain expression. The program transforms this expression, it's formal algebra, and at the end, exec, which means that you calculate it numerically. And the result can be formulated more abstractly more. If you manipulate all these symbols in a purely symbolic way, without resorting to numerical evaluation, you get a certain ring, P, for period, and now you have exec, or evaluation, if you want, which is a map to a certain symbol at the end of the calculation. You transform the symbol or the collection of symbols into real numbers. So you have a ring, P, and you have a homomorphism from P to R. Now, I'll explain this because it's simple to explain. Delin has another version of it, which is more sophisticated, and which has to do with representation of groups. Okay. But it's a little more sophisticated. Okay, so now we have, of course, what everyone expects, well, as a part of project of Grothendieck, that this map is an injection. That means if you have a numerical coincidence between a certain kind of integral, let's say you have zeta, it is known that zeta of 2 is pi squared over 6, which was a great discovery of Euler. Pi itself can be represented as 4 times integral from 0 to 1 dx over 1 plus x squared. So if you multiply pi squared, it's a double integral. So you have a certain double integral is another double equal to another double integral, numerically. There should exist a formal proof. You know that very well. You know that very well. Okay. There should exist a normal, purely formal proof, and indeed, we know a formal proof of it. So the idea is that in all cases it should be similar. When you have a numerical coincidence, you should have an explanation by purely formal algebra, the kind of algebra that has been defined by Zalberg. Okay. Okay. So now, here comes the challenge. The challenge is that in physics, we have also to express, when you want to exploit the quantum theory of fields, you need also to calculate some integral. They are the so-called, they correspond to Feynman. Well, I spoke yesterday about Feynman integral, which are infinite dimensional integrals. That's not what I want to say. Feynman diagrams. For instance, take a simple example. A diagram of this kind. And suppose that your theory has only one field of a scalar field of speed 0 and a mass. Okay. So the point is that in a given, so Lagrangian, which is much more elementary than the real one, the realistic one. So you have a diagram of this kind. There are 3 vertices and 4 edges. You have n vertices and 2n minus 2 vertices and edges. Well, it's just a particular case. They are much more complicated. But these are crucial. When you have to evaluate them numerically, this is crucial. And now what you have is that if you have this, there is a certain diagram, and the technology is a Schwinger parameter. I will not enter into that. But at the end of the day, you reduce it to an explicit geometric integral. So you have the graph. You define a certain, which has vertices, let's say, I'm sorry, you consider variable corresponding to the edges, introduce for each edge a variable. Then you have introduced a certain polynomial psi g, which is the following. Sum over t, the graph is connected. A tree is a subgraph which contains which goes through all the vertices with a minimum number of edges. It is known that the minimum number of edges is n minus 1. So you can connect 3 points by 2 edges, and there are many ways to do that. Each way is a tree. For each tree, you select, for instance, suppose you have selected these 2 edges. They correspond to variable x1 and x2. Then you take the corresponding monomial x1 times x2. And you take the sum of all monomial corresponding to all trees. So of monomials. So it's a certain polynomial, a homogeneous polynomial of degree n minus 1. Now, if you consider the projective space of dimension p 2n minus 3 of R, you want to integrate over here. You can integrate over here, well, omega 2n minus 2n, well, I will not enter into psi g over square. Well, you have to deal with homogeneous coordinates. There is a well-known trick to integrate invariantly. It's called sometimes Gelfand residue, to integrate. If you have a space of dimension, a projective space dimension 2 and minus 3, then you have a differential formula in 2 minus 2 in the corresponding affine space at 2 minus 1. And this is homogeneous of degree 0, and there is something called the Gelfand residue, which tells you how to make you are in to make it transform it as a 2 minus 3 integral. So this integral is obviously a period. So it's a period. Well, you have to be careful about the denominator, but it's a period. It's a period, and this period plays a very important role in the theory, in the evaluation. It's one of the critical things to calculate. I don't have time to develop all the technology, of course. But okay, now what you see is that in quantum theory of field, you have such integral. And they are of the proper kind, So the idea is to promote them as motivic period, or period in this abstract form. So they are real numbers, but you do this. That means you calculate with them without doing numerical analysis, doing purely formal algebra. Okay, so now the point is that, yes. And I finished work, I need 5 minutes to finish. Okay, the point is that behind this, there is a certain group. In the same way as algebraic number can be manipulated by Galois theory, the group of finite group. These, if you, at the moment we can do nothing with so these periods are usually transcendental number. Pi is a transcendental number, zeta 2 is a transcendental number, zeta 3 we don't know. We know it's irrational, but we don't know more. Zeta 5 we know nothing. Zeta 7 we know nothing.
We do know. We don't know a proof. I know.
we don't. At the moment we don't know. Well, all the conjectures are quite clear, but the proof does not exist for the time. So what the point is that doing calculation here would be hopeless. But the point is that if you work at this level, there is a kind of Galois group, a group of symmetry, which is called the motivic Galois group or Grothendieck-Teichmüller group. There are various names. So you have this, the number here are usually transcendental numbers. They cannot be treated by ordinary Galois theory. But if you lift them at this level, and hopefully you do nothing by lifting them, it's faithful, then you have a kind of Galois group. And this group is what plays the role. And now, this group has been recently, the latest paper by Francis Brown, not the latest, I mean, already 2 or 3 years ago, Francis Brown identifies this group. Identifies this group, and it's in the process he solved a conjecture which was suggested by Manin and Gonchao for 20 years. Okay, so he has identified, he has given a proof that, and particularly he has shown, for instance, that the double zeta, let's say the double zeta or multi zeta could all be expressed into special sequence. If you have multi zeta which are only 2 and 3, and the sum of 2 and 3 here, 2 plus 2, 4, 7, 9, 12, A plus B is 12. So he has proven a conjecture which is due to Hoffman, that all multi-zeta value can be expressed linearly as a linear combination with integral coefficient of these numbers, the rational coefficient of these numbers, which was surprising. And more on that, but he proved that if we leave things at this level, these numbers are linearly independent. So we have now a basis of all multi-zeta numbers, not the true numerical one, but the formal one, motivic one. So we have a good control, and there is a group of symmetry, a kind of Galois group. Now, what is the challenge? The challenge is that this has been extended to this situation, which is not really multi-zeta value, which has been extended, and the people who did that was Dirk Kreimer, Francis Brown, and Spencer Bloch, and also Hélène Hénaud. Collaborated, so big collaboration between very good experts in different, Kreimer is a physicist, but the other one are very good experts in algebraic geometry. So it has so they have proven that these periods which are really the realistic one in physics are periods in this sense, and they have identified the corresponding Galois group. Okay, now the challenge was that when I wrote my paper 15 years ago, all examples suggested that these numbers here, corresponding to Feynman graphs, should be multi-zeta value. And it was everyone agreed on that. And there were enormous numerical experiments, mostly by Broadhurst and his collaborators, Kreiber, Broadhurst, which suggested that in every instance, the true value was a multi-zeta value. And then when I wrote my paper, I said, okay, there is here a certain Galois group which has a physical meaning, obviously. There is this Galois group which corresponds to the MZV. They should be related to some extent. They should be related to some extent. But now we know, and Francis Warren discovered very, very explicit example and very good example showing that it is not true. When you calculate this integral, they are not all MCV. They are more complicated transcendental number. Well, the general strategy is not lost because there is a kind of symmetric group for this, but it's not the one we expected, but it's the same idea, And now, to finish, what is a punchline? What is a connection with physics? My idea of a cosmic Galois group is the following. I state it now. In the model, we have 20 constants. These constants are not really constant. They are running constants. That means they are limiting value at low energy. And when you increase the energy, they run, oh well, it's all the technology of the renormalization group. And the renormalization group was put in a much better form by Kreiber and Kohn, which makes the connection with all this development much easier to understand. So this is there's 20 constants. Okay. They ought. What you could expect is that all these constants are running constants. That means there is a certain differential. They correspond to. So there is a parameter. There is a differential equation. So there is a Galois group, and for this differential equation, and then when you specify the parameter to be 0, then you get the value for low energy. Lambda is typical, this variable lambda is a scale of energy. When for lambda equals 0, they are very good. So what you should have is that you should have some differential equation, which are partly understood. For this equation, there should exist a Galois group, which is connected with all these symmetry groups which come here. And at the end, you could merge all this into a unique big group of symmetry, which not only acts on the result of the integration, but also acts on the basic constant. So it suggests that there is a deeper level to explain this constant. That this constant again should be represented by some integral, so there should be a kind of diagrammatic or similar diagrammatic at the moment. No one knows. So what I propose as cosmic Galois group is a kind of a beginning of the beginning of the beginning of an explanation. I'm not quite modest. At the beginning of the beginning of the beginning of the explanation. So you should enlarge the model to include some explanation of this constant by some integral, so you have a deeper level, and this constant should be obtained from a deeper level by suitable integral. And there should be a symmetry group, an overall symmetry group, which should explain why these constants are there. So a kind of Galois group, cosmic Galois group working at the level of elementary particle physics. Thank you.
Are there any questions?
In particular, you would be able to explain one day the 137?
Of course. Many people have tried, but so far, well, at first they thought it was exactly 1/37, but now we know better. We know many digits. It's certainly not a rational number by any means. So.
It's a prime number.
Could we have a show of hands for dinner?